Welcome to Pomodoro Joe for Thursday, October 5th, 2023. Today we're doing LeetCode problem 229. Majority element 2. This is a medium problem. Given an integer array of size n, find all elements that appear more than n divided by 3 times. All right, then we have an example, 3, 2, 3. 3 shows up more than 1/3 of the time, so we get 3. 1, we return 1, 1 and 2. They both appear 50% of the time, so that's more than 1/3, so we return both. All right, so this one seems pretty straightforward. We'll put 25 minutes on the Pomodoro timer and we will get started. So we'll start with our result, and it will be, looks like we need a list of ints. So let me spell result right. We'll have a list and we'll return our result at the end. All right, for this, I think I'm just going to go through the array, go through every number, and count how many times they appear. And to do that, I'll use a dictionary, or in my case, I'll use a default dictionary. So we'll have counts. That's just going to be equal to a default dictionary of int type. And then we'll just go through for every number in our nums. The counts for this number will increase by a 1. So now we have a dictionary that maps the number to the number of times it appears in our array. Now we just have to go through all of these numbers and see which ones appear more than 1/3 of the time. So the length of our nums array here, that's going to be the length of nums. And so our target, we're looking for something that's greater than 1/3. So our target here, that's going to be length of nums divided by 3. All right, and now we just go through for every num in our counts. If the counts for this num are greater than this target, well then this is one of our numbers. So our result will just append this num. Cool. And then we get to the end, we return our results. All right, that's pretty straightforward. Let's see if this works. Okay, it seems to work. Let's see if we can pass all the tests. And we pass, just like that. And we do pretty well. We beat 51% for runtime and 64 or 84, let me see. 51% for runtime and 84% for memory, so that's not bad at all. All right, let's jump back here really quick. If we wanted to gain a little bit more speed, we could probably eliminate this length nums here. So we could do this. And we might even do an integer divide instead of a floating point divide by 3. Let's see if this helps. And it gives us a little bit of a boost. Now we're at 84% for runtime and 49% for memory. So yeah, a nice little boost. All right, one last thing. This is perfectly acceptable. This is a great solution, very simple, very straightforward. However, they do have this little follow-up here. Could you solve the problem in linear time and in O of 1 space? So linear time means that we can go through the array more than once, but we can't go through the array depending, how do I put this? We can't go through the array a number of times that is dependent upon the size of the input array. So we can go through 1, 2, or 3 times, some set number of times, but we can't go through like 10 times if the array is size 10, but 20 times if the array is size 20. That's not linear time. An O of 1 space means that we basically have constant extra space. That means we can't use things like our dictionary because that is going to depend on the size of our input. So there is a way of doing this. It's kind of tricky. I don't expect you really want to see this, but I'll go through it really quick. So let's start this whole thing over. Now the key insight to this one is to understand that we're looking for numbers that appear more than 1/3 of the time. So how many numbers can there be that appear more than 1/3 of the time? Well, if we have one that appears more than 1/3 of the time and a second that appears more than 1/3 of the time, well, that takes up 2/3 of our numbers. There can't be a third number that appears more than 1/3 of the time. So in that case, our return value will be at most 2 numbers. So we can still have a result. I guess it's not totally O of 1 space because it does depend on the input a little bit. It'll either be 1 or 2 elements, but it's pretty small. Okay. So we'll still have a result. We'll still return our result at the end. But now, instead of going through and counting all of our numbers. We'll go through the array one time, keeping track of the frequency of our number. So to do this, we'll basically have some number. When we get to a number that we haven't seen, we'll start tracking how many times we see that number. If we see numbers that aren't that number, then we'll start decreasing its frequency by 1 for every new number. So essentially we're going to build up a frequency and then drop it back down in the case that we're not seeing the number as frequently. So in the end, when we do build this up, we should have two numbers where their frequency is greater than all the other numbers. So let's start with this. We'll have n1, which is our first number, and we don't know what it is yet, so we just set it to none. Then we have n2, that's our second number, also equal to none. Now we'll keep track of the frequency. The frequency of 1, we haven't seen any numbers yet, so it's 0, and frequency of number 2 is also 0. All right, so this is constant extra space, just a couple of variables here. Now for every number in our nums, this is where we have to do a little bit of mental gymnastics, but here's the idea. If our frequency for number 1 is equal to 0, so that means that we don't actually have a number 1 anymore. So if this frequency for this number is 0, then we can set our number 1 equal to this num. And we can set our frequency for this num equal to 1. So now we have one number of this num. All right. Otherwise, else if our frequency for number 2 is equal to 0. So if we already have a number 1, maybe we have a number 2 that we're looking for. So if our frequency for number 2 is equal to 0, then we can set number 2 equal to this num, and our frequency for this number is equal to 1. Now, we do have a slight problem with this. We could run into a frequency where this is 0, but it actually is the same number as number 2. So let's say we had, how do I describe this? We could be going through, we build up frequency for number 1, and then it drops down to 0 because we don't see that number anymore. So we could end up with a frequency for number 1 while we still have some number 2. And then when we run across a new number 2, or a new instance of that same number, number 2, then we're going to see frequency for 0, and we're going to assign number 1 to the same number as number 2, which means we're going to keep the same number but counting its frequency in two different places. That's going to be a problem. So we only want to do this if, so frequency is 0 and num2 is not equal to this number, or maybe I should say this number is not equal to num2. And same thing down here. If we get to frequency of 2 is 0, we want to make sure that we're not storing num1 here. So, and n is not equal to num1. All right, otherwise, actually I should say else if this number is number 1, well then we can increase our frequency for number 1. So number 1's frequency gets increased by 1. And let's see, if number is number 2, then our frequency for number 2 goes up by 1. And otherwise, if it's neither of these numbers, it's not number 1, it's not number 2, then we need to decrease their frequencies. This is some new number, so frequency for 1 gets reduced by 1, and frequency for 2 gets reduced by 1. So if we start seeing other numbers, they're going to be taking the place of the frequencies here. It's kind of suppressing the frequencies of number 1 and number 2. All right, so that's our first pass. In pass number 1, we're just building up our frequencies for the numbers. So if you notice, we're going to be building up these frequencies, and then if we stop seeing a number, like number 1, we just stop seeing number 1 for a while, we're not going to be increasing its frequency. We're only going to be decreasing its frequency. At some point, it's going to reach 0, and then we'll replace number 1 with some new number. Okay. Now that we have our frequencies, let's actually go through and find out what are the counts for these numbers. So for every number in our nums, let's see, I guess I want to keep counts. So count for number 1 is 0, and count for number 2 is also 0. All right, for every number in our nums, if n is equal to number 1, then our count for number 1 is increased by 1. And if n is equal to number 2, then our count 2 is increased by 1. Now we have the actual counts. Let's make sure that these match our target. So our target will be equal to the length of our nums divided by 3. And if count 1 is greater than our target, well, then we can add it to our result. So we'll add result dot append number 1. And if count 2 is greater than our target, then our result dot append number 2. And again, we return our result to the end. All right, let's see if this works. All right, and that actually works. Let's see if it'll pass all the tests though. And it does pass. And let's see how it does. It does okay. 57% for runtime, 49% for memory. So we actually do better with our dictionary solution than we do with this O of n runtime solution with constant extra space. A little bit surprising. This is actually making me wonder if this is right. Huh, seems right. All right, well, that's it for me. We learned 2 different ways to do this problem. One way using a dictionary, keeping track of the counts. The other way just going through and keeping track of the most frequent numbers that we find in this array. All right, well, I hope that all made sense. I hope you enjoyed this. I hope you had fun. I hope you learned something. I hope you can go out and write better code.